Alright, here we are again for part 2 of today's lecture. Alright, so this is going to be lesson 31 in CENG 3306 Mechanics of Materials. We are again continuing our work in section 7.1 and 7.2 of the Hibbler text, and we have a few learning objectives for this video. 1. Explain the derivation, limitations, and assumptions inherent in the shear stress equations for bending. 2nd, calculate Q for a given cross-section. And 3, calculate the transverse shear stress. Okay, and mainly this is going to consist of just a couple of examples and a few notes on Q, tau, etc. Man, I call it tau. No, it's ta. 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 It's important for silly reasons. Alright, so I know I say I'll write a lot, don't I? Oh well. Alright, let's get started. So, I will I'll label this example 1 here. Example 1. Example 1. Let me make sure we're still rolling them. Oh, it's paranoid. We are. We're good. Excellent. Okay. So, I'm going to be given a certain cross-section, and let me illustrate this, and I'm also given some other information. Let me give you that information first. I am given that this has a V of, it will have another shear load of 50 kips, an I of 136 inches to the fourth, and a Y bar of 5 inches for the neutral axis. So that'll just save us from doing some calculations of 5 inches. Y bar of neutral, so that's the location of the neutral axis. And I'm also given the cross section. So I wouldn't, since I am also being given the cross section, I don't actually need to be given these, but I'm just providing these to make the calculations a little bit faster, just because of our limited time. If you need practice on calculating cross-sections, why don't you try it with this T-shape at home? And these should be the solutions that you get. So we're going to have a cross-section here, a T-shape. So we now have a non-symmetric shape. It is horizontally symmetric, but it is not vertically symmetric. We have a point B here. And then let's see, 2 inches, this thing's going to be, the upper flange is 2 inches. So the way we describe this, we use the same terminology as we do a W section, flange and web. There's not a T section, you can essentially think of it as a W section with only one web, with only one flange. And then this will be, this web is going to be 6 inches tall. The flange is going to be 2 inches thick. That's quite a thick flange. And maybe this is a concrete beam or something. And this is going to be 2 inches. This is going to be 2 inches. And this is going to be 2 inches. So lots of 2 inches here. And B is located right at the web-flange intersection. However, I'm also told that the neutral axis is here at 5 inches. That's the, dang it, I erased part of my web here. I'll have to redraw that. The eraser is dangerous in this tool. Okay, so the neutral axis is going to be here. This is NA. And it is located a distance of 5 inches up the beam. Here. Okay, so I want to calculate, I'm going to have a series of prompts, and I'm going to go through them. Basically, I'm going to have 2 parts. In the first one, they're essentially the same as the previous problem, but we're just going to learn how to work with it for this here. For non-symmetric sections, that's what I wanted to say. Okay, so part A, let us get the shear stress at the neutral axis. At the neutral axis here. So I'm going to do a note on, okay, here's a question. How would it look if I calculated Q both above and below the neutral axis? So first I'm going to calculate it above the neutral axis, and then I'm going to calculate it below the neutral axis and see what happens. So let me first calculate it for a cut above the neutral axis, or a section above the neutral axis. So this would be the neutral axis here. Neutral axis, and here, this would be 1 inch. This is of course the same 2 inches, and then these are 2 inches as here, and this is 6 inches. 6 inches. So it's basically made of a rectangle 1 inch and 2 inch wide, and 6 inch and 2 inches. 1 inch tall and 2 inches wide, and 6 inches wide and 2 inches tall. Now these are each individual piece is going to have a centroid here and here, just at the middle of it. And we know that Q is equal for compound shapes, or composite shapes, is equal to the summation of y bar A, which is then simply equal to, for here, equals 0.5. That's the y bar for the first piece down here. 0.5 inches, and it is measured from the point that we're taking. The distances are always measured from the point that we're interested in the stress at. We're interested in the stress at the neutral axis, so that is why the first piece has a y bar of 0.5 inches. 0.5 inches times 1 inch times 2 inches, that's the area of that piece, plus 2 inches, that'll be the distance from here to the centroid, times 2 inches times 6 inches. Y bar A, sort of a centroid. It's the first moment of area calculation, which is part of the centroid calculation, which is then 25 inches to the third. Now, what if I wanted the Q for the area below the cut, or below the neutral axis? So I'm going to cut it at the same cut. I'm just drawing it a little separately. And this is going to be like this. I'm going to have the neutral axis now located at the top of a section. And let's see what happens. Neutral axis. And the y bar for this is going to be 2.5 inches. And this is going to be 5 inches long for our calculation here. And we will see something very interesting. It's the same formula. So Q equals y bar, which is 2.5, the distance from the neutral axis to the centroid of it, of a piece, times the area, which will just be 5 inches, times 2 inches. Hey, and what do you know? This is 10 inches. 10 times 2.5 is 25. Huh. Would you look at that? It's like I knew it was going to happen. 25 inches to the third and 25 inches to the third. At the neutral axis, well, remember, in elastic bending, the neutral axis is at the centroid, and we remember in centroid that really the definition of centroid, if you remember from statics, is this is baked into it. All the centroid is just this over the area. So it makes perfect sense that the Q above the neutral axis should be equal to the Q below the neutral axis. So if you're taking the stress, if you are taking the stress below, if you're finding the stress at the neutral axis, it doesn't matter whether you take the Q above or below. You can just go ahead and take whichever one's easier. So then finally I can very quickly go through the stress calculation, which will be a very quick procedure. Just simply our nice familiar now, hopefully familiar now, VQ over IT, which is then going to be equal to 50 kips, our shear, times our Q, which we've just found, of 25 inches to the third, all over IT, oh, derp, let me put the numbers, 136 inches to the fourth, times a thickness of 2 inches. And this then equals 4.6 KSI. 4.6 KSI. So that is the stress, the shear stress at the neutral axis. Alright, what about the stress at point B? Here here it is important which direction we choose the Q. B stress, or I should say TAW stress, shear stress at B. So I'm going to do this here. So I'll draw this, and then here, that we're now looking at a point well above the neutral axis. So the neutral axis is here, and it's not really important anymore. B is here, and the outward Q is going to be smaller in this direction, so we're going to base it off of this. So this, in other words, the larger the Q, the higher the shear stress. So we're going to take it this way instead of this way. So now let's consider this. The here. Let us look at this here. Just a moment. Just a moment here. Let me look at something. Here. Here, just let me check something really quick. I'll make sure I showed something right. Yes. Point of note, just something to note. Y bar is always going to be the distance from the neutral axis of the entire shape to the centroid of the piece you're looking at. I don't know if I adequately explained that properly in the last in the last lecture. Y bar is always the distance from the neutral axis to the centroid of the piece you're looking at. So that is important. So then, here, let's look at this. And now, our Q then is simply going to be, so the centroid here, the distance from the centroid of this shape of this rectangle to the neutral axis is going to be 2 inches. And the Q then is going to be equal to 2 inches times 6 inches times 2 inches is then 24 inches to the third. 24 inches to the third. So the Q is the same. Now, here's an interesting thing. What thickness do we use? What thickness do we use? Look at this shape. B is right at the boundary between the flange and the web. So which thickness do we use? Well, the fact is, a transition in the geometry, or more accurately stated, a discontinuity in the geometry will represent a discontinuity in the shear stress. So we have actually two cases. The tau at B at the flange, well, for this, T will equal 6 inches. The tau at B at the web, here the T will equal 2 inches. So for both of these are still both governed by tau equals VQ over IT. The V is the same, the I is the same, the V is the same, the Q is the same, and the I is the same, but the T is not the same. So then we just plug and check on this. Tau is 50 kips times 24 inches to the third over 136 inches to the fourth times 6 inches. And here, ta is then equal to 50 kips times 24 inches to the third over 136 inches to the fourth times 2 inches. Well, this one is going to be 1.47 ksi, and this one is going to be equal to 4.41 ksi. So really, this really shouldn't be that surprising if we think about it. Stress is always, if we go back to the very first principles, stress is always, it's always sort of, I always sort of think of it in terms of base physics or the fundamental definition of pressure. It's obviously not the same thing. Pressure creates stress, as we've seen in pressure vessels and things like that. But some of the same behavior applies in the sense that if you have a greater area, you're going to have, generally, as a general, very sort of vague general rule, if you have a larger area, you're going to have less stress. And this does make sense. So if we have the entire flange resisting the shear stress, well, we get a much greater ability to resist stress, so we have a shear stress of 1.47 ksi. Here we have, if we're looking at the shear stress in just the web, we're going to have a much higher shear stress, literally 3 times greater. So, let us look at the shear stress distribution. So, here, what if I plotted a few shear stress distributions? Shear stress distributions. I'm going to plot 2 shear stress distributions. One I'm going to plot from lesson 30, example 1, which was this one here, the one with the rectangular cross section, and one will be for this problem here. So this is for example 30-1, and you could actually find this just by you could find this graph by taking the shear stress at various locations. So example 30-1, lesson 30, example 1. There's just one example in the previous lecture, but that's okay. So the shear stress distribution for this is going to be like this. Here, we have a rectangular cross-section, and then we have a neutral axis here. Something like this. And then we would have, let me illustrate this. Do my stresses in red like I like to and I remember to. So again, this is the neutral axis. I would have actual shear stress arrows going down. We could think of them as going vertically down here. And the if I plotted them along say a vertical axis instead of a horizontal axis, the relation between shear stress and height, or shear stress and depth, is going to be like this. I'm going to have a parabolic behavior. In this case, it would just be a smooth parabola. And I would have, at the point B we found previously in the last lecture's example, ta is 1.74 ksi. And here, ta max at the neutral axis is 3.13 ksi. All right, and we can note that, of course, this I should note here, you can't always tell by drawings, but this is parabolic, a parabolic curve. Next, I will draw the shear stress distribution for the previous example. Let me actually label that example 31-1 that we're currently in lesson 31, and that was for example 1. So example 1 of lesson 31. And you need to work on the numbering here, I think. But next semester I'll organize these a bit better with different numbers. But that's okay. here, so there were a couple gaps in the numbers, but whatever, that's fine. It's just a number. So here we have our, I will label my neutral axis. And that's totally not to scale, but that's okay. Here's my neutral axis. And then what's next? Let me very lightly, maybe in yellow, just as a tracer line. This line doesn't actually mean anything. All I'm doing is trying to trace the, horizontally trace the discontinuity that we're going to have. So if I plot my shear, and again on the vertical axis here, what will I see? Oh, we got purple and gold here. Well, it's not a. Well, there may be some university with purple and gold, and I hear when I see purple and gold, I think of a small town in Iowa called Waukee, Iowa. It's a town I grew up in, and the colors of their local high school football team are purple and gold. So that's neither here nor there. The Waukee Warriors. So, but that has very little to do with statics. I guess they used some statics when they designed the football stadium, but that has very little to do with statics class. Okay, so we are going to, we'll start with a 0 shear stress at this surface, and then we will parabolically be increasing. We won't have a slope of 0 here, but we'll have a, at this location here, where the web is, where the web begins, we will have 1.74 KSI. Then we will have a jump, a discontinuity to 4.41 KSI. 4.41 KSI. And then we will continue to parabolically increase. And this is not going to be a scale, but that's okay. And here the slope of the increase would be 0. The slope of the curve would be 0 here, just like we would expect for a local maximum. And here tau max is going to be 4.6 KSI. And then, because this is just a smooth rectangle from here on down, we'll just have a, oh my goodness, that looks bad. We will just have a smooth parabola, which I'm going to attempt to draw all the way down until it's 0 on the outer surface. I've drawn worse, as you have seen. And then, you know what, I'm going to try to squeeze one more on here. This isn't an example we've worked, so we don't actually have to work in numbers. But if I just had an I-beam, a W section, and I'm calling it an I-beam now, I am so going to hell for that. A W section here. Here, so if I plot this here, what will this look like? Well, this would actually be just like this, except symmetric. So if I plot the neutral axis in purple, and to make the Waukee Warriors happy, I'm going to plot the discontinuities in yellow here. And I guess Waukee isn't such a small town as it used to be. When I was there, it was still a suburb of, it was still, when I moved there before kindergarten, it was still a very small town, well outside the city, but as the time grew, it became an actual suburb, and kind of got swallowed up in the Des Moines metropolitan area. But that has nothing to do with statics. So this keeps increasing. Sorry, this is just our shear stress arrows in general. We are going to have a parabolic increase to the web flange interface. Then we're going to have a discontinuity. Then we're going to have another parabolic increase, and the slope here wouldn't be 0. It would just be, you know, I'm going to purposely draw it without having a slope of 0, so maybe something more like that. That makes me happy. Then something like this. This would have a slope of 0 right at the maximum. Then we'll have another curve down to here, and If I could draw very good, I would, or if I could draw very well, I'd make this perfectly symmetric, but you all know my drawing ability is not the best, so I will just draw down to here. So something like that. And this would be our Taumax. For ordinary loads, it tends to be and ordinary sections, it tends to be a parabolic distribution. Only broken by discontinuities, or discontinuities in the geometry, I should say. Note here, a few notes, so just points of note. Note tau equals 0 at edge, and this ultimately comes down to Q equals 0. There is no outward first moment of area at the edge, so tau equals 0. And Taumax occurs at the neutral axis, where Q is at maximum. Q is max. Okay, so let us discuss some of the validity of this here, of the shear stress equation. Validity of our shear stress equation. We want to discuss the limitations of it. Validity of shear stress equation of tau equals VQ over IT. It's not information technology, it's not the Stephen King monster it is just the moment of inertia times the thickness at that point. You're like, man, as the semester gets going, the professor gets more and more screwy. Okay, no comment. So we have an assumption that we have a elastic, homogeneous, and constant cross-section. So those are just our beam assumptions, really, or some of them. Constant cross-section. Then, let's see. There's also some limitations on our geometry here. Say, here, and this basically comes out of laboratory analysis, analyzing directly measuring the actual shear stress through, say, strain gauges versus the theory that we've developed, versus the simple theory that we've developed. So, here, D and T. Let's look at a web. If, as long as T over D is less than or equal to 0.5%, we'll have under 3% error. It's basically at 3% error, which for the design of structures and machines is usually fine, because you should have enough factor of safety to take care of that. However, what about webs? So this generally will work pretty well for webs. We can see that the depth versus the thickness, as long as thickness is much less than the depth, this will work fairly well. However, what if we have a wide flange? Very wide flange. Say we have let's look at a flange. Let's say T and D. Well, when we've actually analyzed this, we've found that T over D, if T over D is greater than 2, in other words, it's if you have a very thick flange, or let's say it's like if you have like a very actually I'd have to draw it more like that for a flange, is greater than 2, you might have a 40% error, up to a 40% error, which is quite a bit. That is not acceptable. So, essentially we can actually say, here, we can summarize this by saying that the equations are generally not good for flanges. Not good for flanges. They're not good for flanges. Oh, don't want that. Or for the flange web intersection. Those are stress concentrations. In other words, anywhere you get a discontinuity, that's obviously there's some issues with that. The equations really won't be valid if real materials don't exhibit harsh vertical discontinuities like that. So if you're going to really do something like that, there are equations in, say, steel design that you can design flanges for shear, but they're a bit more involved than our simple equation here. So stress concentration. And let me do a little side note over here. What about irregular sections? Something that didn't follow the nice flange web system. Well, so you had something like this. It's like a curvilinear, maybe it kind of ovate. Looks like there's a flangish thing and a webbish thing. Well, here it would be okay here, but it wouldn't be okay up here. Not okay. So just keep this in mind as you're going through these equations. So let's see. Let's keep going. All right, I have one last example I want to work through today, and we'll see. We'll see how this works. Now, I'm going to just work through one more example, and here, let's look at this. Actually, let me think about this one more. Second. Let me see. Do I want to work through this? Yeah, I think I have time. I can work through this. Okay, we'll just go kind of quick. So, here, let us plot our, let us describe this. This is going to be example 2 for today. We are going to have a beam. It's going to be a simple rectangular beam. And I'm just going to go ahead and give you the reactions. It's going to be a nice friendly beam in reality. I have a 16 kip load right at the middle. I have a 16 kip load. So this is just an example of going all the way from beam diagram to stresses. So say I have this one is going to be a reaction of 8 kips here and a reaction of 8 kips here. And this is a rectangular cross-section. So I'm telling you that it has a rectangular cross-section. And I want to know and it has, so let me give you the dimensions of the cross-section and the dimensions of the beam. That might help first. The length is going to be 72 inches, but the load is right in the middle, and that's why the reactions are symmetric. So we have a load of 36 inches, a dimension of 36 inches and a dimension of 36 inches. Our cross-section has a width of 3 inches, and then and an overall height of 8 inches. However, I am interested in the not the cross section, the shear stress at 3 locations. I'm interested in the shear stress at 3 locations. Let me draw this by 3 lines. First, I already have this pen up, so let me do the B line. Line B is going to be located 2 inches from the top. Line A is going to be located at the neutral axis 4 inches from the top. At the neutral axis, 4 inches from the peak, or from the top of the beam. Oh, this is at point A, and let me indicate in green, this is point B, and then finally in blue, I will indicate point C, which is right on the upper surface of the beam. Like there. Okay. So I'm given all of this nonsense, and I want to determine tau at A, B, and C. So the first thing I'll do is draw the shear diagram. That's my task, determine tau at A, B, and C. Okay, so the first step will be to draw the shear diagram. Draw shear diagram. And this one is not going to be too hard. It's just a point load with 2 equal reactions. This is a nice, simple shear diagram. We can do this in our sleep. So the shear diagram is going to look like this. Now, let's see. So I'm just going to draw this. It's simply going to be like this. We can just do this one by inspection, like this. A, B, and C are well within the left portion of the beam. So this is going to have, this will be a value of 8 kips and negative 8 kips. So this is going to have positive shear, positive like that here. We can think of it like this. And by this I mean positive shear according to the conventional notation I described when we looked at shear and bending moment diagrams. And then this would be negative shear. Here, 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 and here. V as a function of x. So next, so basically we're going to have to design for a V of 8 kips. Now I need to find some Q's. Well, actually, first, even back on this last slide, I think I can squeeze in to find I. That's not that bad. It's just a rectangle. To find I. And I is just equal to 1/12 BH cubed of the cross section, which is then just simply 1/12 times 3 inches times 3 inches times 8 inches to the third equals 128 inches to the fourth, like so. 128 inches to the fourth is I. Then I want to find some Q's. So let me find QA. Actually, I will just find for each of these I'll just go all the way through the problem. So find tau A. Well, to do that we'll find QA. And at A, well, this is at the neutral axis. So we can simply say, we're looking at this region here, at the neutral axis, at point A is here. So, and of course this is 4 inches, the outward area is based on a 4-inch tall area, 4 inches. And so, here then, and 3 inches wide, etc. And the centroid will be 2 inches high. So then I can just go, okay, well, QA is going to be 2 inches times 4 inches by 3 inches. Again, the y bar is the distance from the neutral axis to the centroid of the piece. 4 inches times 3 inches equals 24 inches to the third. And then ta A is going to be 8 kips times 24 inches to the third, all over 128 inches to the third. No, actually 128 inches to the fourth. Sorry about that. That's 128 inches to the fourth times 3 inches equals 0.5 KSI. So that is the shear stress at the neutral axis. Now, I want to find ta B. Find ta B. The shear stress at point B. So the only thing that will change here is the Q at B. So here we have the neutral axis at the middle. But then we have point B here, which I believe I did in green last time. Yes. So I'll do that. So we're looking at the section here. This is point B. So Q is based on the outward section here, which will be 2 inches by 3 inches. And the centroid of this is here. So, let's see. So this is, again, 2 inches by 3 inches, which means our y bar, the distance from here to here, is actually going to be 3 inches. So I can just find QB relatively simply. QB is then 3 inches times 3 inches times 2 inches. The area of that piece is then 18 inches to the third. And ta, I cannot write. Ta today is just 8 kips times 18 inches to the third over 128 inches to the fourth times 3 inches equals then 0.375 KSI, and that is our ta. Okay. And then finally, let us find ta C, and I will plot this after this. Let's do a ta C. Find ta C, the shear stress at C. Well, let's look at this. This is actually going to be fairly simple. Here at C, look at this. There's no area here. There is no area above C. So therefore, area at C equals 0. Therefore, QC is 0. And therefore, since we are using the equation V equals KQ over IT, if Q is in the numerator, then by very simple mathematics, ta C must be 0 KSI. Fairly straightforward. All right. So we have those stresses at those 3 points. Finally, I'd like to just list some general rules of shear stress. For rectangular shapes, there's actually a very simple formula you can use to calculate the shear stress, or the maximum shear stress at least. So if you have rectangular shapes, things are all hunky-dory. There's a word I haven't used in a while. Hunky-dory. Wow. here I have an, not blue, let's do green. I like doing dimensions in green. So let me say boom, boom, boom. Really slap together drawing. This would not pass muster in engineering graphics class, but that's okay. H and T. And then you can actually derive this if you wish. Ta max is just 3/2 V over HT. To derive this, simply find the shear stress at the center or the neutral axis of the centroid or the neutral axis of the rectangular section in terms of V, HT, etc. And that's what you'll find. Okay. And then finally, another note for standard shapes. Let's see. So standard shapes. Let's look at standard shapes. Some of your standard shapes here. One final section. Standard shapes. Here. If I have a, say like a W section, I'm just caught saying I names, oh my goodness. Okay. So our W section here, let us say it will be mainly carrying shear, it'll be carrying shear really only through its web. So the web really carries all the shear load. The shear is carried through here. These cannot transfer any shear, well, they can try to, but we really treat them as carrying all of their shear through the web. So when we're actually calculating shear in steel design, we neglect the flange entirely. Basically, the web carries the shear and the flanges carry the moment. D and thickness of web, TW, T sub W, and the shear stress distribution will look like this. So we model it as saying, oh, the web is carrying all the shear, but in reality, the shear stress actually does decrease in the web. This is why our equations, remember how I said they have high errors in the webs often? Well, really this isn't a problem, because by the nature of webs, the shear stress is going to be very low. So the shear stress tends to be like this. There's a massive increase. I don't like how that looks. Let's do something more like, okay, that's symmetric-ish. Going to there and coming back down. Okay, I can live with that. Something nice and tombstone looking. And this then, at the centroid, is ta max. Okay. So, the ta max is approximately equal to the ta in the web, which is less than or equal to ta allowable. So again, even though we know there is a great deal of error in our shear calculation at the flanges, ultimately it really doesn't matter because the web is carrying all of the shear anyway. So these equations are actually fine. If I ask you for the shear at some location in a web, just use these equations, even though we realize there's some error into it, and that's fine. It's not critical there anyway. Over a web equals V over, so we can think of it like this, d T web is less than or equal to ta allow, which is equal to often ta yield over the factor of safety. That's F capital S. So really, this is our governing equation for most, say, steel design and concrete design. Your shear over your depth of the beam times the thickness of the web must be less than or equal to ta allowable, which is often equal to the yield stress of the material divided by the factor of safety. All right, that will do it for today. I hope you enjoyed the lesson. If you have any questions, feel free to email me, and we will be back at it tomorrow for yet another lovely day of CENG 3306 Mechanics of Materials, and as always, thank you.